Welcome to part 3 of my lecture series on pseudo-transients and how they're used to solve steady-state CFD calculations. In this part of the lecture series, I'm going to be carrying on from part 2 of the lecture series by talking about the characteristic speed in fluid domains and how it's calculated and how this is different to solid domains. In a fluid domain, there are a lot more flow physics that we need to account for, and we have to account for the effects of convection, diffusion, and possibly even buoyancy forces and compressibility. And we need to know all this information and use it when we specify the characteristic speed in fluid domains. This is the final part of the lecture series, and I'm going to be wrapping everything up and bringing everything together. So if you're excited to solidify all your knowledge about pseudo-transients and CFD and finish off the lecture series, let's jump into the talk. So, kicking things off with a quick recap of what we talked about in part 1 and part 2, the pseudo-transient approach is a method that's used to stabilize steady-state CFD calculations. And the way it carries out this stabilization is by adding an artificial term to the diagonal of the A matrix in the steady-state matrix equation, and also an additional source term to the right-hand side of the matrix. And the size of the artificial or pseudo time step delta t controls the increase in the diagonal terms of the A matrix. And the smaller we make the pseudo time step, the more iterations it's going to take for our steady state calculation to converge, but the larger the diagonal term in the A matrix is going to be, and that will increase the stability of the solution algorithm. So how do we specify the pseudo time step size? Well, the first approach would be to do something similar to what we did with relaxation, where we just arbitrarily choose a value of the pseudo time step. And that approach could work, but it doesn't generalize very well to lots of different CFD cases. And what we'd actually like to do is to get the CFD code to specify and calculate the pseudo time step size automatically. And that's been the focus of the past few talks. So how would a CFD code go about specifying a pseudo time step? Well, what it does is it's going to take into account some of the physical properties of the domain that we're solving, and that allows the pseudo-transient approach to vary on a case-by-case basis. Now, if we took the example of the backward-facing step flow that I've used in the past few talks, what we would do is we would estimate the time taken for the effect of the boundaries to propagate across the domain. And in this case, for example, if we have an inlet boundary here on the left and an outlet boundary here on the right, and we made some estimation that it would take of order 10 seconds for the effect of this boundary or the change in this boundary to propagate across the domain, then we could take a fraction of this time and use that for the pseudo time step in our pseudo-transient CFD calculation. So the big question arises, how do we estimate the propagation time for the effect of boundaries to propagate across the domain? The way that the CFD code does this automatically is it calculates the propagation time as the characteristic length of the domain divided by the characteristic speed that the effect of boundaries propagates across the domain. And we looked at these two quantities in part 2, and I showed you how to calculate L0 for a general CFD domain of an arbitrary shape and size. And we also looked at U0, or the characteristic speed for the effect of the boundary to propagate across the domain. And we looked at this for the special case of solids. And the reason that we did that is because solid domains are very simple, because we only need to worry about how the effect of heat is transferred across solid domains in the energy equation. And what I'm going to be doing in part 3 in this talk is I'm going to be focusing on the calculation of U0, the characteristic speed for fluid domains. Because fluid domains are more complex, we have more physics going on, and there's also a greater variety of different flow behaviors within the domain that we need to be able to take account of. But the general principle is still the same. We specify the characteristic length of the domain using the techniques that I went through in part 2, and then we calculate the characteristic speed that the effect of boundaries propagate across the domain. We divide one by the other. That gives us the propagation time, or the characteristic time, and then we use a fraction of that to specify the pseudo time step, and we use that to iterate through our steady state calculation until we achieve a converged steady state solution that doesn't vary with more iterations or more pseudo time steps. So the way I'm going to motivate this talk in part 3 is just to start with a simple conceptual idea to help you understand the differences between solid and fluid domains. And what I want you to do is just consider the two domains that I've got here on the slide. They've both got an identical shape, and they both be passed to the CFD solver with an identical mesh in them as well. However, the difference between them is that we're going to specify the domain on the left is steel or another solid, and the domain on the right is water. So one is a fluid, one is a solid, but otherwise they're identical in shape and the mesh that they have. How is the characteristic speed going to be different for these two domains, and how would the CFD domain calculate it depending on if we specified it as a solid or as a fluid? Well, if we look at solids first, just a quick recap of what we specified in part 2 in the last talk. With solids, we only need to think about the propagation of heat with the energy equation, and the effect of boundaries in a solid propagates by diffusion or conduction. They both mean the same thing, and we looked at that in the previous talk. So in solid domains, we only need to think about the process of diffusion, and we can use the formulas that we used in part 2 to work out what that characteristic speed will be for the propagation across a solid. Now, in a fluid domain, we also need to think about the effect of convection, because the background fluid or the background molecules in the domain, you can think of it that way, are moving across the domain from one boundary to the other. So our characteristic speed is going to be based on the effect of both diffusion and convection. So we've got two different physical transport mechanisms that we need to account for when we pass this domain to the CFD solver and we say, this is a fluid domain, calculate my characteristic speed so I can specify my pseudo time step in this particular domain. So I'm going to start by just talking about diffusion in fluid domains and just considering this as an extension of how we considered diffusion in solid domains, and then I'm going to go on to talk about convection and how we address that. And just to recap for you, in the previous talk we derived this formula for the characteristic speed in a solid domain for the propagation of thermal energy. And the formula we use is the thermal diffusivity, alpha, which has units of meter squared per second. And this is a material property. It's taken as the average thermal diffusivity across the entire solid domain. And we know this before even starting the CFD calculation. And we divide that by the characteristic length of that solid domain. So meter squared per second and 1 over meter gives the correct units of meter per second, which we want. And this formula is applicable for a solid domain, but perhaps is there something similar that we could use for a fluid domain because we're considering the same transport mechanism? Well, what I want you to do is just think for a minute about the physical property known as kinematic viscosity. Now, the kinematic viscosity is the dynamic viscosity, which is often given the symbol mu, divided by the density of the fluid. And this physical property has units of meters squared per second. And you'll remember from the previous slide that these are the same units that we just saw for the thermal diffusivity as well. So these properties are related in some way. They're similar and they capture similar mechanisms. And we can immediately see this is the case because as well as being described as kinematic viscosity, nu is also known as the momentum diffusivity. So we considered the thermal diffusivity for the solid domain, and nu is also known as the momentum diffusivity. It has the same units, and what it's really telling us is it's related to the characteristic speed that momentum is transported across a fluid domain rather than heat was transported across a solid domain, which we saw in the previous talk. And we can just use this direct analogy to derive a formula immediately. We saw for the solid domain, the characteristic speed u was just alpha over L naught, but for a fluid domain, we can use the kinematic viscosity divided by L naught, and that will give us the characteristic speed that momentum is propagated across the fluid domain. Now, some of you, of course, will notice that the thermal diffusivity is a material property. We can prescribe it for solids, we can also prescribe it for fluids, and so this is the characteristic speed that would be transporting energy across the domain, or thermal energy. But when we consider fluid domains, our fluid domain may be isothermal, and that means that it may be at constant temperature, and so this wouldn't be the best formula to use for fluid domains, particularly if we're considering an isothermal flow problem. And so this is actually the better formula to use for fluids, because it covers the case where fluids are heated, when they're thermal fluids, and when they're at constant temperature, or when they're isothermal as well. And for the majority of fluids that are considered, which have a Prandtl number of around 1, then actually the kinematic viscosity and the thermal diffusivity are relatively similar quantities anyway. And so you could use alpha instead for the fluid domain for fluids like air and water, and you'd get a similar answer. But that's just a small caveat. It's not really important. The main thinking point is that we've just derived a characteristic speed for how momentum propagates through a fluid domain by diffusion. And what I'd like to do, just to make this formula consistent with other formulas that you may see in CFD manuals, if we just substitute in the definition of the kinematic viscosity, that's the dynamic viscosity divided by the density, we arrive at this formula for the characteristic speed for diffusion in fluids. And this is going to be a reasonably good formula for flows at low Reynolds numbers. So creeping flows and flows with Reynolds numbers less than 1, this is going to be a very useful formula and give a good representation of the characteristic speed that the effect of boundaries propagates through the domain. And in the same way that we did for the thermal diffusivity, of course, the dynamic viscosity and the density are taken as averages over the entire domain, because we only need a representative speed for how how the effect of boundaries propagate through the domain. And so just a quick recap, how would we actually calculate the characteristic speed for diffusion in a fluid domain? Well, what we do is we start at the start of our calculation before our CFD code has even pressed go yet, and we just take the average of the dynamic viscosity and the density over the domain, and then we use the equation above to calculate a characteristic speed for diffusion, and then we use equation 8 where we divide the characteristic length scale by the characteristic speed and take a fraction of that, and that will give us the pseudo time step that we can then increment through our steady state calculation with. And I just wanted to give you a quick example of actually using that formula so you can really see what the numbers actually turn out like. And the example I'm going to consider is just a box, a 1 meter box containing air in this case. And the boundary we're going to consider is this velocity inlet on the left hand side, where flow of air is moving into the box at 1 meter per second, and then it's going to move out of the box 1 meter away again at 1 meter per second. And so if we wanted to calculate a characteristic speed and a pseudo time step for this CFD calculation, the first thing we would do is we would take the dynamic viscosity of the air, which is given there in the formula, and then the density and the characteristic length for this domain is obviously a meter. Plug those into the formula, and we find that the characteristic speed for diffusion is 1.5 times 10 to the minus 5 meters per second. So immediately this is telling us that the characteristic speed for diffusion is often very low. And if we don't have a creeping flow or a flow at low Reynolds numbers, this is going to be a very slow velocity. And if we were to use this, this would actually give a very large pseudo time step, which is not what we want. And for this particular example, just common sense tells us that actually a better speed to use for the propagation of boundaries through the domain is actually the inlet velocity. We expect the effect of this inlet velocity to propagate across the domain from the inlet to the outlet at 1 meter per second. We don't expect it to go at 1.5 times 10 to the minus 5 meter per second. And so what we need to do is we need to carry out an additional calculation, which is going to be to determine the characteristic speed for convection in fluid domains as well. So we're going to be taking into account convection and diffusion. And actually the specification of the characteristic speed for convection is a bit more involved than you might first expect. And how I want to illustrate this is if you consider this domain that you can see here on the slide, you can see that I've chosen something that has quite a complex shape. The flow weaves around some bends, and there are some recirculation regions and regions where the flow turns corners. And so this flow actually has a complex shape, and the velocity is going to be varying all over the domain. It's not necessarily going to come in at that 1 meter per second that we saw in the example on the previous slide. So as the velocity varies everywhere, what velocity should we take for the characteristic speed in this domain? We can calculate the characteristic speed for diffusion directly using that previous formula, but what's the characteristic speed for convection here? Well, the trick is to actually think back to our formula for the pseudo time step and notice that because the characteristic speed is on the bottom of the fraction, we want to use the highest velocity in the domain, or something that's representative of the highest velocity in the domain, because that's going to give the smallest pseudo time step and therefore the greatest increase in the diagonal dominance of the A matrix and the most stable calculation. So what we want to be doing is looking at our domain and thinking, where is the characteristic speed and what would be a good representation for that characteristic speed? Now, the first domain I want you to think about is this simple example here, which has a small inlet, a small outlet, and then the flow moves out into a very large space, like a tank, for example, or an open room full of air. And remembering from that previous slide, we want to use the highest velocity for our characteristic speed. And for this particular domain, it's clear if this was an incompressible flow at constant temperature, that actually the flow would come in and it rapidly expands into this room where it's going to be very slow moving. And the highest velocity in this case is actually on the boundaries of the domain, the inlet and the outlet. And so for this domain, we could quite happily specify the inlet velocity as our characteristic speed. And that would be the same that we used for the example with the box of air. But what if I took the other extreme? And what if I said, we have an incompressible flow at constant temperature again, and this time the flow has a large inlet, a large outlet, and then a constriction in the middle of the domain. Clearly for this example, the highest velocity is going to occur in this constriction. And we could use some indication using conservation of mass to work out what we think a representative velocity might be for this constricted region in here. And that would actually be a better choice of the characteristic speed for convection for this particular domain. So you can start to see already that there is some variation in the characteristic speed between different CFD domains, and actually the shape of the CFD domain and what's going on inside is actually going to govern what a good choice of the characteristic speed would be. And the approach that I'm going to introduce here is the approach that's often stated in the CFD user manuals, and I've just put a note in the description of this video about the relevant section in the ANSYS CFX user manual, which explains this as well. So if you have access to that user manual, that's a good place to look. And if not, if you use another CFD code and you look in the manual for that code, you should see a similar explanation for the characteristic speed and the pseudo time step calculation. And what you'll see is that for general domains, what CFD codes will often do is take the largest velocity on the boundaries, also look at the largest velocity in the domains, and then take whichever is larger of these two velocities and use that for the characteristic speed. And that will then, of course, ensure that regardless of what the shape of the CFD domain is, if this is an incompressible flow at constant temperature, then we'll be using the largest characteristic speed and the smallest pseudo time step. But of course, what if the flow that's inside our domain has some different flow physics? All I've talked about so far are simple flows, incompressible flows at constant temperature. What if we had a compressible flow, for example? Well, from our knowledge of physics and compressible flow, we know that in a flow that's significantly compressible, depending on the Mach number, the speed of sound in the domain may be faster than the local flow speed. And so for compressible flows, it would also be a good idea if we took into account the speed of sound in the domain. And actually, a volume average or some kind of average of the speed of sound over the domain would also be a good choice for a characteristic speed in these domains. And if we had our previous examples where the Mach number was very low, of course the speed of sound would be very low as well, and therefore the characteristic speed based on the speed of sound would be a lot smaller anyway, and it wouldn't be chosen. So I can actually combine all of these characteristic speeds that we've just talked about together into one convenient expression, and that's there in equation 12. You can see I've got the characteristic speed for diffusion there at the start, the largest velocity on the boundary, the largest velocity in the mesh, and then the average speed of sound throughout the domain. And so what the CFD code is actually doing here is before you start the calculation, it's going to go ahead and calculate what each of these characteristic speeds are, and then it will take the largest value and use that for the characteristic speed for the entire domain. And this is a fantastic approach because it means the user doesn't actually have to say to the CFD code before you start, by the way, this is a compressible flow, or by the way, this is a creeping flow at low Reynolds number. The CFD code can just calculate all of these velocities and then just take the largest one, and that will automatically account for the regime or the type of flow that's going on in the domain. And so this treatment is general and it covers a wide range of flows. And the largest speed, once again, will mean that we take the smallest pseudo time step size in the domain. And before I carry on with the talk, I just wanted to make a small side tangent and talk for a little bit about the Reynolds number and the Mach number, because you'll see how this actually comes in to the specification of these characteristic speeds. If you recall, the general definition of a Reynolds number is a density multiplied by a velocity multiplied by a length scale divided by a dynamic viscosity. That's the general definition of a Reynolds number. Now, if you rearrange this slightly and just move the characteristic velocity there outside and then collect the other terms together in the brackets, what you'll see is that this quantity here is actually 1 divided by, or the inverse, of the characteristic speed for diffusion that we calculated earlier in the talk. And so when you look at the Reynolds number here, a way you could interpret it for this particular talk is the Reynolds number being the ratio of the characteristic speed for convection and the characteristic speed for diffusion. And so if the Reynolds number is greater than 1, what it's telling you for this talk is that the effect of boundaries is going to propagate across the domain faster by convection than it would for diffusion. And of course the opposite holds true as well. If the characteristic speed for diffusion is larger than the characteristic speed for convection, then the Reynolds number would be less than 1. And the effect of that boundary is going to propagate much faster by diffusion than convection. And so if you have a look at the expression there, equation 16, that we put together for the characteristic speed for the domain, if the CFD code calculates all of these values and the characteristic speed for diffusion here happens to be larger than the maximum velocity on the boundary and the maximum velocity in the mesh, then that implicitly means that the Reynolds number is probably going to be less than 1. And the same holds true with the speed of sound as well. If the average speed of sound happens to be greater than the maximum velocity in the mesh and the maximum velocity on the boundary, then that means that the Mach number is likely to be greater than 1 for the CFD domain. And so this expression is really accounting for and is able to account for differences in Reynolds number and Mach number. By calculating all of these speeds individually and then taking the maximum, we're automatically identifying and choosing the right characteristic speed depending on the Reynolds number and the Mach number. Because intuitively we would expect, looking at a flow, that if the Mach number is greater than 1, then the effect of boundaries will propagate at the speed of sound and not at the speed of diffusion, for example. So this formula is actually really clever and actually accounts for differences in Reynolds number and Mach number, which is why the approach is so general, and the CFD code can just use it, and the user doesn't need to tell the CFD code what type of flow is going on in the domain. And another advantage of this approach, of course, is that we can extend it to account for other types of flows that I haven't talked about in the talk today, because I've only talked about low Reynolds number, moderate Reynolds number, and compressible flows. You may have, for example, in your case, you may have a flow with significant rotation, where, for example, the flow domain is being driven around by some rotating body force, and if, depending on the speed of that rotation, that speed may also be a better speed to use for the characteristic flow velocity in the domain. And we may also have interesting flow physics going on in the domain. We may have buoyancy-driven forces from temperature or density differences, and the velocity from that buoyancy force may be the dominant force in the domain, and a velocity scale based on that effect may be a better velocity scale to use for the characteristic speed in the domain. But the fantastic thing about that formula that we described and went through previously is that we could calculate a characteristic speed of rotation, a characteristic speed for buoyancy, and then just put that in the previous formula and take the maximum value, which would either be this new characteristic velocity or the characteristic speed of diffusion or the characteristic speed of convection. The approach is completely general and can be extended to cover different types of flows that I haven't talked about here. And if you're interested in these characteristic speeds for rotation, buoyancy, and other types of forces that I haven't talked about here, they can often be found in the CFD user manual. And the ANSYS CFX user manual, which I've just linked in the description, that's also got discussion of how you calculate the effects of rotation and buoyancy as well. But hopefully for this talk, you get an appreciation of the method of approach that the CFD code uses to calculate the velocity scale so that you really get that good understanding. And the final caveat I wanted to make here as well is that often CFD codes will just let you specify the pseudo time step directly yourself. So you could also go through these calculations by yourself, calculate the characteristic speed of buoyancy, a characteristic length scale for the shape of the domain, and then specify your pseudo time step yourself. That option is often left open to the user as well, but in most cases we like the CFD code to be set up with some automatic defaults so that the user doesn't have to think about these things for complex cases. So just to wrap up the talk, I wanted to finish with just a summary to remind you of that overall process that the CFD code is going to be going through when you use the pseudo-transient approach. The first step, in the same way as the solid domain, is to just look at the shape of that CFD domain that we've got, ignore the mesh, and calculate a representative length for it, which will either be the cube root of the volume or the maximum dimension of the domain or some other user-specified length scale. Then what the CFD code will do is identify whether the domain is a solid domain or a fluid domain, and if the domain is a fluid domain, it will then calculate representative speeds for convection, diffusion, compressibility, and buoyancy, rotation, all of the other forces that may be applied to that domain. And then it will take the maximum of those representative speeds to be the representative speed that the effective boundaries will propagate through the domain. And then once it has these, the CFD code will then divide the characteristic length scale by the characteristic speed and take a fraction of this time and use that for the pseudo time step in that particular domain. And thinking back to part one of this talk, just as a reminder that the pseudo-transient approach can use different pseudo time steps in different domains. So that means this process will then be repeated for the next domain. If we have a conjugate heat transfer domain, for example, we'll consider the fluid domain, then the solid domain, then the next fluid domain, and this process will be repeated for each of those domains, and a different pseudo time step can be specified in each of those domains so that those solutions develop at different rates and allow us to approach that steady state solution in an efficient manner. And of course, the only difference here for the solid domains is that when the CFD code identifies that it has a solid domain, it only needs to calculate the representative speed due to diffusion, because of course the solid is usually stationary and we don't have any background movement of the solid itself. So that brings me to the end of my lecture series on pseudo-transients as a method for solving steady-state CFD calculations. I'm really hoping, now that you're at the end of this lecture series, that you've got a much better understanding of how the CFD code actually calculates this pseudo time step size and what it means and how it can be used to improve the convergence of steady-state CFD calculations. If you're looking for more information, I highly recommend opening up your CFD user manual and flicking to the page or the section that describes pseudo-transients, because you'll find a lot of this information and more detail about how your specific CFD code calculates characteristic lengths and characteristic speeds, for example. And also let me know in the comment section, how did you find the talk and the series of lectures? Did you enjoy it? Do you find this style of lectures useful for you, going in a lot more detail about how different parameters in the CFD code work? Let me know in the comment section. I do really enjoy hearing from you, and I like hearing your feedback as well on the lecture talks. Until next time, thank you all very much for supporting the channel, and I'll see you in the next video.